is they give us the table, and we need to say if the relationship's a linear function. And so remember, linear functions from previous years in math, we know that they have a constant rate of change, and they would make a straight line when you graph them. And so we need to then put it into words, an equation, and a graph. And they already give us the table, which is really nice. And so the trapezoid example is definitely like a level 4 or an advanced problem. And these are going to help us build up to understanding that problem even better. So given our table 1, 5, 2, 10, 3, 15, 4, 20, let's figure out what is our rate of change. So remember, we always have x's and y's, or input, output. Inputs are x's, outputs are y's. So as our y's, we are going up by 5, plus 5, plus 5, and our time is going up by 1 each time, plus 1, plus 1. So in each time, when you take a rate of change, remember rate of change is y over x, we are always having 5 over 1, 5 over 1, 5 over 1. And they're all the same, so that's our rate of change. We can say either 5 over 1, or we could just say 5. It's going up by a constant of 5. So right already, I know because it's a constant rate of change, it is linear. Linear, yes. Next, we need a graph. Remember to label time and height. And so at 1, our height is 5. At 2, the height is 10. At 3, 15. At 4, it's 20. And if you graph with a ruler, yes, we get a straight line. So the equation, remember, we're basically going off of this y equals mx plus b. M is our slope, or rate of change, and b is our y-intercept, or when x is 0, what would your y be? And in this case, it's 0. So our equation is y equals m, which is 5x, plus our b is 0, because notice that it's right there. So we could just actually write y equals 5x. And then if we were going to put this into words, we would say to multiply the time by 5 to find height. And we're not adding anything, so we don't need to say add anything. So now we have another example, same as last time, and first we're going to find our rate of change. And remember, rate of change is y divided by x. So we have our time is x, our height is y. 4 to 3, we minus 1. 1 to 2, we add 1. 3 to 5, adding 2, but 2 to 3 is still adding 1. 5 to 7, adding 2, adding 1. And so if you find the rate of change, we have negative 1 over 1, 2 over 1, and 2 over 1. Are all 3 rates of change equal? This one is not equal. And so because we don't have a constant rate of change, it is non-linear. So we can go ahead and graph still. 1, 4, 2, 3, 3, 5, 4, 7. But that's definitely not a linear graph. There's a definitely turn in there. And so because it's not linear, we're not going to worry with an equation or words. So now go ahead and try example 3 on your own. Remember, start with rate of change, find your rate of change, then graph. And once it's graphed, write your equation in words. And don't forget to label. We're going to have hours on the bottom of our graph and total rain on the y-axis. So go ahead, solve, see if it's linear, and if it is, write your equation, words, and rate of change. And don't forget, equation is y equals mx plus b. Go ahead and compare your solution with mine. Notice I found it was linear. I have my rate of change, an equation, I put it into words, and I have my graph, which is a straight line, with my labeled axes. And next, in example 4, we're given ordered pairs, and we need to figure out if it's a linear function and explain how we know. So I like to go ahead and graph it first. So I'm going to assume everyone's a 1. So -2, 1, 2, -3, 1, 2, 3. Right there. 0, -1, 1, 0, 3, 2, 1, 2, 3, and 4, 4. So, graphing alone, that's not really a straight line to hit all my points, so I'm going to say no, that it's not linear. But I'm also going to double check it and find what is my rate of change and is it constant. So here, add 2, okay. Here, add 1, well, that's the same so far. Add 2, add 2, add 2, add 1. So if I put them all as fractions, 2 over 2, 1 over 1, 2 over 2, and 2 over 1. Well, this becomes 1 over 1, this becomes 1 over 1. These three are the same. This one is an oddball, though. It simplifies to just 2. And so my rate of change is not constant, so I'm confident now that it's not a linear function. Because sometimes your graphing is not exact, and so that's why it's always good to look at rate of change also. And so I know it's not linear because graph is not straight line, and rate of change is not constant. So both of those prove that it is not a linear function. Go ahead and try example 5 on your own and make sure that you look not only at the graph but also at the rate of change to determine is it a linear function, yes or no. Notice that I have it graphed and it looks like a straight line, but at the same time, maybe I should have curved it a little more. I'm truly not sure if it is a linear function or not. So, because my graph doesn't clearly show us, remember we're also going to look at our rate of change. Notice when comparing my rates of change, 1/2, 1/2, 1, and 2, they're not equal. So it is not a linear function. And so my explanation would become that my rate of change was not constant. And maybe if I had a bigger graph, or if I was using paper, my graph would be more clearly defined. But that was pretty hard to tell from, and so it's really important that you look at your rate of change to see if it's linear or not. In example 6, we have to complete the table to see if it's linear. And so we're going to try to do this without graphing. And so they give us an equation, and what we need to do is we need to plug in our value of x into the equation and find y. Input, output. So I have 2 times -3 plus 3. Well, 2 times -3 is -6. -6 plus 3 is -3. And you're going to do that for the remainder of the table. So notice that my table has been filled out, and we need to determine if it's linear or not. Well, let's figure out what is our rate of change. We add 4, add 4, add 4, add 2, add 2, add 2. So we have 4 over 2, 4 over 2, 4 over 2. They're all the same, so yes, it is linear. Constant rate of change. Go ahead and try example 7 on your own, then check back to see if it's linear or not. I have my chart filled in and I went from 21 to 5 to 5 to 21. Just looking at it, because my numbers went up by 2 always on the other side, I know it's not linear. Also remember, you can always double check by finding the gaps and your rate of change, and it's a non-constant rate of change, and it's just clearly not linear. And finally, I want you to look at and analyze these two. The one on the left, y equals 2x plus b3, was linear. So it was linear. And the one on the right, y equals 2x squared plus 3, was nonlinear. Now notice that they're basically the same thing. We have y, we have a y, we have 2, 2, we have a 3 and a 3, and finally, notice what's different. We have an x and an x squared. One thing to observe is that linear will always have only an x. Nonlinear, they will have an x squared, x cubed, or x to the whatever, but it's not going to be just an x. When you see an exponent, then it's going to become a nonlinear function. So just an x is linear, x with an exponent becomes nonlinear.